So, how do satellites know where they are? There are actually two completely separate dimensions that we need to consider with satellites. First, orbital parameters. It describes the movement of satellite over time in 3 dimensions. Second, attitude, which basically tells what direction the satellite is facing. It is entirely independent of location for satellites because there is no natural state that a satellite is expected to be in. On Earth, the natural state for attitude is aligned with gravity, basically upright. Satellites have no such force or natural state to adhere to.
Determining where a spacecraft is pointed is therefore an exact science and is simply known as attitude determination. Attitude cannot be measured directly by any single measurement, and so must be estimated from a set of measurements that can be done either statically, calculating the attitude using only the measurements currently available, or through the use of a statistical filter, most commonly the Kalman filter. This combines the previous attitude estimates with current sensor measurements to obtain an optimal estimate of the current attitude. Using any of the two above approaches requires the use of attitude sensors. So, what are attitude sensors? Basically, attitude sensors sense the position or orientation of fields, objects, or other phenomena outside the spacecraft. The most common attitude sensors are magnetometers, sun sensors, and star cameras.
Magnetometers are used by satellites when they are within Earth's magnetic field. This is a very low fidelity measurement though, so it's typically not used by itself. Sun sensors are photodiodes that measure light intensity. By putting these sensors in several places surrounding the satellite, we can measure light incident on each sensor, giving us the direction of the sun, which when combined with location data can give us a pointing accuracy of 10 degrees or less. Star cameras are the primary means of precise attitude measurement for spacecrafts. Stars are far enough away from us and moving slowly enough that we can treat them as constant or motionless, except in the rare cases which require utmost precision, of course. This means we can create a map of the star field that surrounds Earth, and we can reference it to calculate exactly where a camera mounted on the satellite is pointing. Horizon sensors. On the Apollo program, special horizon sensors were used. They could use the Earth's or the Moon's horizon and plot where it was, and that would be one of their points of reference to determine where the spacecraft was pointed.
Inertial Measurement Unit, or IMU, can sense the rotation of the spacecraft and the acceleration. Once attitude of the spacecraft at a particular epoch is known, an IMU can determine where you are pointed after some time has elapsed. The initial position and attitude, however, of the spacecraft is periodically updated because a small amount of inaccuracy can build up in IMU measurements over time. Using this continuous information from the IMU, it is possible to make any needed attitude changes whenever required using attitude control mechanisms.
Now that we know how to determine the attitude of a satellite, a natural follow-up question arises. How do we control it? Satellites again have a problem that they exist in literal vacuum. So you can't really use a steering, rudder, or flaps. The attitude is therefore controlled using conservation of angular momentum. Satellites make use of this through a technology called onboard reaction wheels. The subsystem onboard a satellite responsible for determining and controlling attitude is called Attitude Determination and Control System, or ADCS.